Hello everyone, and welcome to our presentation on our work Vallr, a visual ASR language model for lip reading, where we focus on visual speech recognition or lip reading without the use of audio signals. Lip reading, or visual automatic speech recognition, aims to interpret spoken language purely from visual cues like lip motion and facial expression. This is an inherently difficult task because many phonemes share similar visual appearance. For example, P and B look nearly identical visually. Therefore, our goal was to improve visual-only ASR. Existing end-to-end systems require massive quantities of data in order to train these models, while audio-visual models depend on the addition of large-scale audio datasets as well. Therefore, our goal was to create a visual-only solution that remains data efficient, interpretable, and accurate. Therefore, the key idea behind our model is separating the problem into two stages. The first stage is using a visual model to predict a list of phonemes from a video input, and then the second stage is generating a coherent sentence from these phonemes using a fine-tuned LLM. By using an LLM, we can leverage the linguistic context to resolve ambiguities in the sentence, and we can replace any missed phonemes from the visual encoder. Our model architecture consists of two main pipelines. The first is a vision transformer encoder, or VIT, with a temporal adapter and CTC head, which maps the video frames to a sequence of phonemes. The second stage is a LoRa fine-tuned large language model, specifically the Llama 3.2 3 billion parameter model, which recreates sentences from this string of generated phonemes. Each stage is trained separately, with CTC loss being used to train the phoneme prediction and cross-entropy loss to train the text reconstruction. In order to train the video encoder, lip-reading sentences 2 and 3 are used for the first stage, and Wiki's text is used to fine-tune the LLM. On the LRS3 benchmark, Vallr achieves state-of-the-art performance, and on LRS2, Vallr achieves a comparable result. Specifically, Vallr obtains a word error rate of 18.7 for lip-reading sentences 3, as shown on the right-hand side table, with only 30 hours of labeled data, and 20.8 on lip-reading sentences 2 with just 28 hours of data. This shows that even with just 0.6% of the data, Vallr can achieve state-of-the-art results on visual speech recognition tasks. So here we can analyze where Vallr succeeds and where it struggles. In the correct examples shown here, the model was able to accurately predict all the phonemes in this sentence and then accurately recreate the sentence from this list of phonemes. The video on the right shows the input frames used to generate the sentences, and then the table in the bottom, the column on the left shows the string of predicted phonemes, and then the column on the right shows the generated sentence. As we can see, the model is capable of correctly generating the subtitles. Here we can analyze some of the error cases of the model. The confusion matrix on the right shows the most common failed predictions for the visual encoder, and mostly they lie around similar phoneme sounds. For example, P and B, the different types of E sounds you can make, so on and so forth. And then in the figure in the bottom left, we can see how even with mistakes in the predicted phoneme string, the large language model is capable of still generating a mostly correct sentence. However, as we can see, there are some errors. For example, your and you are can still be incorrectly generated despite the correct phonemes. So next we move on to different ablation studies that we completed for this paper. So the first was removing the phonemes and training the model end to end. This increased the word error rate up to 30.7%, showing that the approach we used was the correct approach. And then on the right, in the graph on the top right, we can see the effect of increasing the amount of data. So by increasing the amount of visual data, we had limited to no effect on the word error rate, whilst increasing the amount of data used to fine-tune the LLM had an effect but not a huge effect. Finally, we can see in the table on the bottom right that using larger language models had the most pronounced effect on the model's word error rate. So, in conclusion, Vallr is the first phoneme-centric large language model-based framework for visual speech recognition. It achieves state-of-the-art results whilst using only 0.6% of the data required by other methods. However, the field remains challenging, with challenges including distinguishing visually similar phonemes, for example, again, P and B, and handling homophones. So yeah, thank you for listening. This has been our presentation on Vallr.